All right, so this is going to be our lecture on odometry. So the general idea is that this delta represents change. So then we can represent the change of the robot as a vector of the change of the x, the change of the y, the change of the z, and the change of the theta. Okay, this looks really complicated. It's just the change of all of the different components of the robot's position. So then we can also represent this as the change of the robot is equal to whatever pose it's at now, subtract whatever pose we started from. Then we can go through that for each I iteration, and the delta at each I is the pose final at each I minus the pose initial at that I, where I would contain that x, y, z, and theta. So now, to represent this, if we have our pose final, pose initial, we can take our pose delta theta, where that is our rotation delta. So we're initially pointing straight up, and then now we're pointing to the right. Then we have our change in x, which is just this bottom, and then our change in y. And we don't need the change in z for this exact situation because there's no z that we actually need to deal with. So, what are encoders? Encoders are tools to track position over time. And there's some different types. There's light ones, which is what's showing here on the left, and magnetic ones, which are more typically absolute. So essentially what happens is relative will always start at a point and it will count. And it's basically just going through and making, tallies for every tick that has passed. Whereas absolute location knows where it is at all times on that 360-degree radius or a 360-degree rotation. So relative can only track over a certain amount of time. Absolute always knows where it is. So this is what they kind of look like. And this is for a quadrature encoder, which is a relative controller. So basically, if A comes before B, you can tell that it is traveling this way. If B comes before A, it goes the other way. There we go. And then it'll count basically when both of these are false. That's when it would count. So you can see how relative ones may get off sometimes and off very quickly, because if output B comes before output A, well, we can tell it's traveling counterclockwise, but it can go the other way. And depending on how many of these like blocks you have per rotation, it can get very inaccurate very fast. So for some formula you should know, we're going to suggest a constant ticks per rotation. So that's basically if you have a encoder, and let's just say it's like 1, 2, 3, 4, 5, 6, 7, 8. Like 8 equally spaced ticks, essentially, which will tell you how fast it's rotating, where it's rotating, what it's at now. The circumference is just going to be pi times the diameter, and the diameter is that inside of the circle. Ticks per inch is going to be ticks per rotation, right? Where that's our constant times our gear ratio, okay, and then divided by our circumference. And what that gives us is it gives us basically an unravel this circle. And now we lay out our ticks like this. And there we go. And now we can find out, okay, where is an inch? Okay, where is 2 inches on here? And then based on that, then what we can do is we can multiply that by our target inches, because we would get, like, for this example, this includes no math, but we would get 4 TPI. Then we can multiply that by our target ticks, and we could get our target inches, and we could get target ticks. Then for ticks per degree, it's the same thing. We just divide it over by 360 degrees. So why would we use dead wheels? Well, mechanism wheels slip, and they slip pretty frequently, and that can lead to lost localization. Mechanism using those four dead wheels, or using just the four powered wheels, often ends in estimates and not accurate odometry. And the math becomes super strange with those vectored wheels because of that slip factor. Three dead wheels are much more accurate. And typically they're placed in this order because if you think about rotating about your center point, right, you can tell exactly where you're rotating, when you're strafing, pretty much anything. So it's way more accurate to do three. But also, two is not a bad option. So then you can see an example up here. There's a roller right here and a roller right here. Typically, Omni wheels are used for these dead wheels, but instead of just using one, you use two and offset them so you can get traction at all steps. Because the way that Omni wheels look, they're like this, and then they have the little rollers, right? And what the rollers do is they provide contact and traction with the ground at that small area. So you can see we're missing bits, like right here. We're missing little areas where we don't have any traction. So what do we do then? Well, we add another one, and we can fill in all of those areas by offsetting it. And there we go. Now we have full traction on the ground. Another thing with this is springing the wheels down. So essentially, it would be like if you connected this little part to something, to just a block. And what that does is it pulls this side up while also pushing this into the ground. What that does is it also helps provide full traction over all viability and over every single place you could be. Now, this would get weird if you were on terrain, right? Like if you're on, little bumps in the ground or you have to get over something, that's going to get really bad really fast. And there's really not any good ways to fix that except for the next idea we'll introduce, which is sensor fusion. This is useful to maintain accurate localization over a long period of time, right? Because what we want to do is there's going to be some sum of error over the entire duration of when we're running the robot. Except we want to minimize that, right? Because if we end up with a foot of error, well, now we have no clue where we are. Ending with an inch or two of error is way better because now we're only off by an inch or two. Whereas with vision, we can get more accurate wheel localization over time. And April tags can give position if calibrated correctly. So this is an April tag. What these are used for is they can give you, basically if your robot's looking at it from here, right, it can see that and it can tell you, okay, you're probably at this location. Whereas, and one drawback to this is it has to be calibrated properly, and it has to be calibrated pretty much perfectly. You also need to know all the offsets from where your camera is, which becomes a little bit strange sometimes, but that's okay. But Kalman filtering or other low pass filters can be used to combine positions, which are essentially just position estimators. And they, in a mathematical way, they guess where you are, or you can treat whatever the April tag gives you as the truth and just say, oh yeah, roadrunner dot position is equal to whatever the April tag gave us. So, what are relative movements? This is generally seen as the start of odometry or autonomous movement, but all of the movements like right, forward, left, or back, provided they have some value for distance. Without the feedback, we can estimate position as current pose plus the direction, right? So we have our current start pose, and we want to go right by 10. Well, now we have our new pose, which is just right by 10. This is really bad because we assume the robot made it there. We assume it didn't hit anything, and we assume it didn't slip, which is very much so improbable in the lens of FTC. So feedback is built in through encoders and odometry, which is also known as localization, which tells us where the robot actually is. However, it may be inaccurate sometimes, but that's what all this tuning is for. So if we make all this big mathematical notation, all this is saying is from the very start until the final time, we sum up all of the error. Therefore, the goal is to minimize our error over the entire time. If you only need to localize for 30 seconds just for the auto, drift and error accumulation is not going to be that big of a deal. And typically, you get more error with more time. This is kind of the way things go, is if you're getting off by, 5 feet over 5 minutes, well, that's only a foot a minute, right? And that's only half a foot every 30 seconds. So when you minimize that, you should be fine as long as you can get it to the point where it's minimal and your error is generally correct most of the time. So let's talk about some two dead wheel odometry. So as you can see here, we have our center of rotation, our perpendicular wheel, which is just down. You can see that this one is perpendicular to the robot's forward. And then we have our parallel wheel, which is parallel to the robot's x direction. So essentially what this does, you can also see there's one up here, but we're going to only take the example of two. Why they put them in this order is a very interesting discussion, right? Because if you have some robot with a center, the thing's back here, one of them's up here, that will actually track your position way better than if you just have that one on the bottom and one at this center point. That's because when you turn in a straight circle, or a perfect circle around the center of rotation, right? It gets very difficult for that perpendicular wheel to see any difference of change from that parallel wheel. And that's the hard part with tracking and localization, because we start to get into singularity zone and where we don't actually know what exactly is happening with our two dead wheels. However, things can help us with this. You can see we have one here, one here. This is probably one of the best ways to track it, just because it allows us to have full telltale control of exactly what the robot is doing when. But even then, we have tools like the pinpoint from GoBuilda, which are able to give us it does all the math for you, right? You just plug in an I2C port to your robot, and it gives you the XY position of your robot at any given time. That is really cool because that means that we don't have to do any of the math, which generally doesn't take that much. However, it does take a little bit of processing power. So moving on to 3 dead wheel odometry, it's generally better overall, just because you have 3 wheels that are all giving feedback and tracking. One other thing I wanted to show real quick is this track width. Essentially, you're going to see this if you're doing Roadrunner. It's the center to center of the wheels. And there's a very big difference between the track width and like the actual track width, because certain adjustments need to be made in order for it to be correct, right? Like if your robot is slightly off, or one of your measurements for these wheels is slightly off, well then you have to compensate for it somewhere else, and track width usually is where that gets compensated for. So I hope this lecture was useful, but thank you for watching.